This opens Class EE 569 on Friday, September 6, 2013.
Okay, good morning. So we'll start the lecture. Okay, quiet. I heard from TA there are not many students going to see the TA during the office hours. So I don't know the reason. So either one, you know what to do, you started and you feel everything is fine. Or second, you haven't started. But I have to tell you, really give you a very clear warning message. If you don't start, if you didn't start last week, you got to start now. Otherwise, you will regret. 100% sure you'll regret if you start to work next week. Your life will be like in hell. Just tell you, I heard so many students saying that. Last week, they focused on the homework because it's due, and then last week. But then first, you will not be able to finish it. Okay, number one, you will not be able to finish it. For most people, and for people who extremely capable, but you really cannot sleep much. And then don't blame other people. Because you shrink the 3-week homework into 1 week. That's the price you pay. Okay, so I really have to give you a very clear warning message. You got to start immediately. Okay, after class, after lecture, you need to start homework. And I can only say so much. That's very, very heavy already. But if you still don't want to do that, I know students sometimes just always driven by the need. There's something more urgent, you focus on that. Something more urgent, you focus on that. So the homework, you say, well, still 2 weeks. But then you will be extremely difficult situation. And that's the reason you don't do well. Some students do well in the class, some students don't do well. The major difference is whether you are able to self-regulate. Sort of it's a self-regulation, self-discipline. Self-discipline. Actually, I see students of two kinds of character. One student, they control their own pace. They are in the driving seat, they handle things ahead of game, do the things according to their own agenda. Then they are not sort of very impulsive. And this student usually will do much better in the career, in their job, in many things, GPA and so on. And another student just driven by the environment. So the environment become tough, they respond more, right? The environment become easy, they don't work hard. So then you always have to go to the tough environment to give your potential out. Otherwise, you go to easy environment, your potential just will not develop. But 569 is an extremely tough course. Okay, I have to tell you, particularly about the implementation and so on. I keep thinking whether I should change the homework pace by every week do one problem. But after a while, I feel you are a graduate student. You're not undergraduate. Why should I treat you like kindergarten kids? Why should I do that? Right? So I want to give you some flexibility. Otherwise, I just say, well, submit every one problem by the end of 1 week. Okay? So you submit one by one, and the grader can check whether you submit or not. But then they grade all 3 problems at the same time. I don't know. If you want me to do that, I can make adjustment in homework number 2. Okay? But I will have to see how many of you really need someone put something on your back, just like watching you like a kindergarten teacher. If you don't behave, then I'm forced to do that. But anyway, I got the feedback from TA, so I'm very, very concerned about how many of you, just not started. So let me ask a question and give me the honest answer. Okay. So how many of you have not yet started? So I asked a good question, right? So I mean, everyone started. Okay, so don't blame at the end. Okay? I assume everyone started and you are doing well so that you don't need to see the TA. Okay, so that's my assumption. Okay, so I will finish the homework number 1 today. So it means after the end of the lecture, you should be able to do the whole entire homework 1. So you still have 2 weeks to finish it. Okay. Again, I have to say, if you follow what I say closely in the lectures, you will be equipped with many, many skills. And then that gives you a great value, add you a great value when you go to the job market. Okay, so you will be very attractive in terms of your skills. But if you just treat this as just one normal course and impulsive and just respond the 3rd week of the homework, at the end, if you learn something within a very short period of time, you forget it quickly. But you learn more in a more uniform, distributed way, just regularly you learn something, then you will remember much better. Okay? So last week, actually, we focused on 2 things. One is about the image I/O, so the image file I/O. Basically, it's try to do the input, how you read the image file, and how you write the image file. Okay, so there is certain format, and then there is some code provide to you. So you should be able to read and write files. And the simplest homework is about the blue screen. So blue screen basically, you have to do some small differentiation using the color so that you are able to separate it. So you can read part of the file. So you are able to select. You are able to select part of file and write it. Right? So that's about try to really it's a very simple idea, blue screen, but just really try to practice, ask you to practice how you read part of the file. Some particular location you can read the gray label or read the color, right? And then ask you to write things. And you can, from different sources, and you can put, say you have input from 2 or multiple files. You have file number 1, file number 2. For example, you have so there's a Superman, and there's some kind of dog, right? Jumping dog. So you have 2 files. Then how you combine the 2 files together into one output file? So you have multiple input files. You are able to read the right content and put there. So there is actually no processing. You just have to access the certain pixel location, get the gray label or RGB, and put on the output. So this is the problem number 1 in the homework number 1. So that's about the I/O. Okay. Then the second part, last week we talked about really how we adjust the intensity level of images. So the image we say is poor contrast. It's poor contrast means the dynamic range of the gray label is within a very narrow range. So when we talk about 8-bit gray label images, the dynamic range of the gray label is from 0 to 255. So totally you have 256 labels. But some images you do not use all the gray labels. You use a part of it. So sometimes you use just the very dark regions. 0 means the darkest. 255 means the brightest white. So use part of it. You don't use the entire gray label. You don't use them sort of uniformly. So then I teach you ad hoc way. Means basically we have so we have histogram of the input file. So there is called H, and then this is input, and the output we call it G, and we can study the input file, the histogram. Okay, we study the histogram and see its distributions. And the output we sort of, if you want, usually we want a uniform histogram. Uniform, we want the histogram to be occupy all possible gray labels, and one of them has the same number of pixels. So same number of pixels, the total number of pixels, suppose you have the n square image size, n columns and n rows. Okay, so n columns, n rows, totally is n square pixels. So then the histogram will be like 0 to 255, and then the same number, this number is n squared divided by 256. Right? Total pixel number divided by the 256. So it's a uniform histogram. So how you go from this, an arbitrary histogram, how you go to there, right? Go get to the uniform. So this is a technique called histogram equalization. And the simplest idea actually discrete one. And actually I told you at the end, so they're discrete. And the way to do that is you just cascade all this kind of bin. So starting from gray label 0 to 55, you cascade them right into a long array. Well, this is a concept, but you can implement in an easy way. Okay, you can use just a counter. So if you assume each one is a bar. Gray label 0, there is a bar, right? And then the bar means how many what's the pixel number has this gray label 0. So then you cascade this kind of bar. And this bar size, the length of the bar will vary. Sometimes it can be empty. If there is no certain grade level, there is nothing, it's empty, then you jump to the next one. So you can basically cascade them, so there's a 0, 1, 2, something, until the final one. So how many pixels here? Eventually still n squared, right? You're adding all the lengths. The total length will be the total number of pixels in the image. So if you count from here at the end, totally will be n squared. And to do this one, the algorithm basically easy is for the grade level 0, I want the bar with this height. So I want n squared divided by 256. So I want has this long bar. Now I divide it uniformly by 256. I cut it uniformly, 256. Each one, the first one will be grade level 0, the second one grade level 1, and so on. Does that make sense? So that's really the discrete case. It's very easy to understand. Actually, we just put things from the lowest, from darkest to the brightest, form a long stream, right? And then divide this stream into uniform segment. And each segment you assign from darkest 0 and 1 and 2 until 255. That's it. So this is so-called the digital implementation. But in the sort of in the continuous form, and somehow there is a sort of transformation. The one grade level only mapped to 1. If you do 1-by-1 mapping, then say 0 has to map only by another value, 1 has to map. Just one input grade level mapped to the one output grade level. In that case, sometimes you will get a stretch. Sometimes the two adjacent grade level will be stretched. Why? Because there are too many, so that there will be nothing in the middle. So then you will stretch. So that kind of thing, you get some kind of empty space. So suppose originally your histogram is very focused on these regions, but after the histogram equalization, you keep the shape, you keep this bar shape, but then the bar distance will become split. So there will be some 0 here, 0 here, 0 here, 0 here, something like that. And so it doesn't look like uniform, but actually if you consider averaging, if you cut this into smaller segments and fill it here, then you'll be like this guy, right? But because you only require one input that has to map to one output, 1-to-1, then you will get this kind of effect. So you get some spacing. But this spacing is actually not good because you will see the artificial contour because the gap becomes bigger. This gap is 1, right? Grade level, the distance is 1. But now the distance can be greater than 1. Particularly the longer bar, then you force the neighbor grade level to be 0. Okay, so then you start to see artificial gap. Okay, so this is not good. Okay, this is better. But in terms of implementation, this is so easy to understand. This is actually a little bit hard to understand. Okay, this is like you through the calculus and so on, right? So this is like more continuous version, but this is a discrete version. But the discrete version actually just so intuitive. You look at that, okay, what else can you do? Of course, this way, right? Okay, so this is about histogram equalization. Any questions about this? And then you're asked to do that in the homework number 2. And you also asked to do some linear scaling.
How to determine the order of the elements in one bar? I mean, the same value, there's many pixels in the same value.
Oh, the order, actually the order, you need one systematic way to do it. There is, I will not say something better than other, but the order usually we do the row-wise order. So yeah, so each one, there is a pixel associated with this grade level 0, right? So you just search from first row, finish, go to second row, third row, and then first 0 will come to first place. And then second 0, you go to second 0, go to the second place, just according to the row-wise scanning order. So order these pixels. That's it. But it's just the one way, okay? Any other questions?
What if you made each of those blocks like small enough to be one intensity on the histogram? Then wouldn't it always be equal?
What do you mean? You n squared equal to 56? That image will be very small.
Yeah. So if you, like, when you're equalizing it, you just made each of those blocks equal to just one spot on the x, for the intensities. So like one block is just like the 0 intensity, and the next block is like the 1 intensity. Wouldn't it? If you have the pixels like that, then wouldn't that always be perfectly equal?
So you talk about block is this block, or this is the, according to the input images. You cannot control that. You just depend on the input images. So your input images, you look at the input images and look at how many pixels and what their locations with grade label 0. You just scan that, and then you scan 1, scan 2, and so on. So that's not something you can control. But output you want to control. Output you want to the block size, the segment size to be the same, identical. So that means histogram will be uniform. Okay. Yes?
Suppose there are 10 pixels having grayscale 0. So when we store it in a single array, so we should be storing the coordinates of.
Yeah, we say location. We scale. We store the locations. Locations.
So we take 2 bytes. I mean, 2 bytes.
Yeah. So this one, each one is a location in this array, the position. When you look at histogram, you only count numbers. That's it. But when you do this kind of equalization, you really have to know where it is. Okay? So today we will talk about the next topic called denoising. So I think it's 1.2. So, first we talk about there will be two type of noise, two-type noise. Okay. At least that's something we can handle well. So one is so-called impulse noise. And one is called usually we call it a Gaussian noise. Impulse noise, that usually comes from the two sources. So one is you have some sensor. Usually when you have a camera, you have a sensor, you can sense the sensor pixels. You try to sense the light for a pixel location. So sometimes you have a dye sensor. Dye sensor. So you have some sensor which is sort of already dying, not functional. So then the output will be black. So the output will be black. You are not able to get the light. Another is sort of called saturated. Saturated sensor dot. Sensor dot. So this sensor already go beyond its full range. So it's just becomes like a white. So it's a white dot. So this gives you a black dot and white dot. And usually we have a name for this. If the black dot, we call it a pepper. So the black pepper, right? Pepper. So we call this as a pepper noise. So just see an image with some black dot in the images, randomly distributed. Okay, so pepper noise. And the white dot, we call it salt, okay? Salt noise. Salt usually is white. Paper can be white paper, black paper, but here paper just means black, okay? So salt is a white dot. So you have image, sometimes you have black dot, sometimes you have white dot. Sometimes you have both. You have black dot plus white dot. And we call this a paper and salt noise. So if you have both exist, this is called the paper and salt noise. So we want to remove this noise, and this is somehow related to statistics. So this relates to the idea called outlier removal. So when you have statistics and you have some outliers, and how you handle the outlier. Okay. So this kind of impulse noise removal algorithm it's really related to sort of outlier removal. So we try to remove the outlier. So there are a few methods, but I will just talk a couple of them. So one is so-called outlier detection. Okay, and once you can detect the outlier, you can remove the outlier. Right? So say there are two major methods. So one is called outlier detection and removal. So the way we do that is we have input images. So this is image pixels. So here I will talk about the window method. Basically, we try to consider window size, and suppose we want to handle certain pixels, we just use the center of the window to cover the pixel of interest. So suppose there is a so this is something we are doing, say, 01, 02. So this is the 3 by 3 window. And center is here, X. So we put this 3 by 3 window, scan through all the pixel location of the input images. So the first one, the window should come here. Okay, but well, what the pixel value here? You don't have pixel value because this image boundary, right? And usually we can do so-called duplicate, so-called image extension. So the way we do that, sometimes we have several ways. One is to copy this, the first row, copy it here, just duplicate. We copy this, just the entire row, we copy this one, and then the entire column, we copy here. So entire column, we copy to the boundary, outside the image, we copy it. And this location, actually, this location is you copy it and you copy it. So actually, these 3 pixels all have the same value as this guy. So copy twice, so copy up and copy left. Similarly, you can do the right boundary. The right boundary, you can copy the rightmost column to the outside one. Okay, so this is called the image extension. And how many additional column, additional row you need to extend? It depends on the window size. If the window is 5 by 5, then you have to extend 2 more columns or 2 more rows, right? But if 7 by 7, then you have to extend 3 more, and so on. Okay, so then well, after the image extension, we are able to create some pseudo pixel values. Okay, then we start using this window, scan this guy first. And once we finish, we move this window, center at this one, and then move around it, and so on. So that's the processing we are doing. So this is so-called local window-based processing, local processing. And this is the most common processing you encounter in this course. So all the image processing, actually, you are doing just there is a window of operators. So this is usually the window, and this window describing some kind of location of the pixels and what you want to do with this. Okay. So the outlier detection and removal. First, we look at this window. And the algorithm is simple. You just try to check the center location X and its surrounding A neighbors and see the value difference. So we check. So we check this one. We calculate the center subtract its A neighbors averaging. So we divide by A, sorry. So you sum all the OI, I equal 1, 2, 3 until 8, and divide by 8. So it's the averaging of the surrounding and compare with its center. If this greater than certain threshold, probably we shouldn't put this epsilon, epsilon means small, certain threshold, T, and if it's greater than that, then we claim X is the outlier. Okay, and then, so that's a detection. And how to choose this T? Then again, you need to learn from some examples. So suppose you can, looking at your particular images, and you can try or calculate these values and plot the histogram of this. And then you can select some part to see this. Indeed, you can find the outlier, okay? Because the outlier location is either 0 or 255. The surrounding are not, right? And those kind of things you are able to check. So you are able to see the T. If the outlier is particular, is 0 and 255, it's easier. But sometimes it may not be reached to that degree. Sometimes outlier may be not 0, not 255, but it's close. So anyway, you can look at the histogram of this distribution and decide what the threshold you should choose. Okay. And once you decide this T, then you check this. And if this is greater than T, you claim X is outlier. And once it's an outlier, you can find the new value, so we call this a reconstructed value, is assigned to be this one. So this is called reconstructed value. Okay, so first you look at the center and look at surrounding nearest neighbor and look at the average and compare them. And usually, if not the outlier, they should be close. But if they are very different, that means this guy will be an outlier. So then I use the mean, I use the average to replace that. So that's a very simple idea, so the outlier detection removal. And then another one often used in statistics is called the median filter. Median and the mean, I think you know the mean, right? But the median also is a simple concept. Median basically says you have some input, a set of, usually it's odd numbers. So it's a set consisting of odd numbers and all numbers of, say, of elements. So suppose you have 3 elements or 5 elements or 10, 11 and something. And then you can order them from the smallest. Say you have the N0, N1 until N, say Nk. And this is in order list. Order the list. So from the smallest to the largest. And the median value, basically, if you have all numbers, you just pick the number in the middle. Okay, the number in the middle. So in this case, we can select median of the sequence. Suppose this is S. S is this sequence. The median will be the Nk divided by 2 plus 1, I think, yeah. Let me rewrite. Is that right? So if 0, 10 will be 5. So then it seems like this. Okay. Right, okay, yeah. Any questions? Say, if you have 0 to k, then k should be even, right? Because total number will be odd. Total number will be odd, so k will be even. So k equals 10, for example. Then you want to pick n equal n6. N6 will be in the middle, right? So then k divided by 5, 5 is the middle, right? Right, 5 is the middle, so k divided by 2, right? Yeah, so that's this, basically is the middle one. Okay, so n with the index is the k divided by 2. So let me give you an example. I mean, it's an easy one. So suppose you have S is like 1, 1, 3, 5, 6, 9, say 100. So in this case, it doesn't matter you have 100, 1,000, or 10,000 here. The median still what? The median still 5. So this is good for the outlier removal. So if so here maybe you can add some outliers, minus 1,000, minus 10,000. It doesn't matter. You will not care about those kind of extreme case. But mean is different. Mean, the outlier can dominate. So something very big, the mean will see that influence on the mean. So median is more robust. So median really look at the entire distribution and pick something in the middle according to the distributions. So outlier will not have any impact to the order, okay, to the median locations. So this kind of median filtering, it's interesting and it can be applied in several things. Actually, the textbook shows some median filtering effect. Let me show you some example from the book. Okay. So operator, can you zoom into this? So suppose this is a 1D input sequence. Okay, and then let's look, we apply the mean and apply the median. And here, the mean filter size is 5 points, okay, 5 points. So if we consider these points and consider the 5 points, so we need to have the extension. So it's the same height here and same height there. So if you have the 5 point, this one will be the same. This one will be the same because the 5 point, this one and these two are the same, right? You just imagine it's extended. Okay? But this point start to have a mean effect. It's 1 high bar and 4 short bars. So you start to raise up. And these two have 2 high bar, 3 short bar, right? And this one has 3 high bar, 2 short bar. So there's you do the average, you have a sort of smooth transition until you reach which point? Until you reach this one, right? Reach this one, it's all left, 2 left, and this right, all high. So now it becomes constant. So from here to here, there's a transition. Okay? And below that and higher than that, you're constant. So there is a transition. So you have a sharp boundary, step function. Usually we call this a step function. It becomes a ramp if you do the mean. But if you do median, actually, you will keep this step function. The way to do that, look at that, is starting from this guy, okay, starting from this guy. This guy, you have 1 long, 4 short, so it's still short, right? This one, 3 short, 2 long, it's still itself. Come to here, 3 long one, 2 short, so it's long. Can you follow me? You have total 5. And if you have 3 short, 2 long, the median will be short. So and then you go over that, 3 long, 2 short, the median will be long, right? So you pass the boundary, you're still just a binary because there are only 2 choices. So the median will be either long or short, right? So in this case, you do the median filter, you preserve the step function. But if you do mean, you smooth it, okay? So that's the price you pay. And if you have the ramp, it doesn't matter, okay? If you have this guy, the impact will be, when you involve this guy in the averaging, you raise it up. Everyone sort of raise up. But when you do the median, this guy will be killed. No matter what, you just 1. The other will be 4, right? So when 4 and 1, the 1 will be eliminated, right? The 2 also will be eliminated. But this 2 will have raised the mean in the neighbors. 3, of course, but once 3, then if you have filter size 5, then you are able to preserve the 3. So when you are in this point, the center in this point, you have the 3 long, 1, 2 short, so it's self, right? This one's 3 long, 2 short, and this one 3 long, 2 short. So it's all stay until you center here. You center here, 3 short, 2 long. It's cut off. But you can preserve all this kind of shape quite well. Okay? So that's the median filter. And another thing for this example, this can be a good problem for the midterm, right? I just give you some kind of input function, and you have to do the median and the mean in your brain. Yes? Actually, this is tricky, okay? This is a good question. For the 1D, actually, it's easy. For 2D, I will show you some 2D examples next page. And it's a tricky business, okay, I have to say. So actually, I feel this kind of things is very ad hoc. It's very hard to do something deep. So on one hand, there are some image processes called ad hoc image processing. Ad hoc is just some experience and so on. And I think you still have to know. You still have to know the ad hoc experience because those are not the difficult things. They're easy to observe. But if you want to do something deeper, it's very hard to build upon that. The foundation is very shaky. Okay? So I just want to show you some ad hoc rules. But you have to know. Okay? Sometimes you say, you don't even know this. Then can forget even something more advanced. So first you have no knowledge, then you have some ad hoc knowledge, then you have some advanced knowledge. Advanced knowledge usually has more deep root in math. And if something only stays in the ad hoc, cannot be really developed into a sort of mathematical framework, you just cannot go too far. Just cannot go too far, so it's very tough. So those kind of things, hard to build the science, okay? But deep science usually require good math. So anyway, these are all ad hoc observation, but give you some feeling about what's going on, okay? So there's a triangle input. When you do the median, when you do the mean, you make this triangle to become like a circular shape. So it's smooth, right? So something very sharp, but you do the mean, you sort of make the transition become more smoother here. But if you do the median, you cut the top one, and the rest you sort of preserve. So this is also very hard to predict, okay? And this is just, you do it, you will find this. But can you generalize something? I just have to tell you it's very hard to generalize anything. So it's just some experience. Okay, now to go to 2D. 2D even more challenging, okay? So these are 2D examples. So suppose you are looking at binary images. So there are just two gray labels. So one in the middle, one in the outbound, out region. So there's square and outside square. The square is, say, black, and outside is white. If you do the filter, you choose the two kinds of filter. It's all 9 points. One is a square filter shape, one is a cross filter shape. And you count them, it's all 9 points. Okay. So you apply this 9 3x3 windows. If you go to this one window, so this one you should be, what's the majority? White, right? Because there are 5 white, 4 black. So this will be replaced by the white. The output will be like that. You come to this second one, you look at the window, now it's 6 black, 3 white, so it's fine. So eventually, the 4 corner point will be cut because the outer, there are 5 outer white pixels, but inner only 4. So you cut these 4 corners. Actually, this is something, in most cases, you don't like that. You want to preserve this. But if you change the filter to be the cross one, 5 and 5 with 1 overlap in the middle, now you look at this guy. 5 and 5. Now you have the 3 black and the 2, so you have 5 black, 4 white. So now you keep black. So now you preserve. Then you can ask me, so what kind of general rule we can get? It's just hard. I don't have any general rule. You just have, but I don't suggest you waste too much time here. Okay? We just stop here. This is an ad hoc topic. And you have some experience, that's it. And I do not encourage you to dig in more about this. Okay, and so one is called the median filter, and one is called the outlier detection and removal. So these are the two major methods. So in homework, you will be asked to do things like this. You will have some kind of paper saw noise, and you need to handle it. Okay. Then the next topic is the second noise type. It's some kind of Gaussian noise, or sometimes you can also consider uniform noise. So just the image plus some noise, okay? And how you remove this noise. So one, it's impulse noise. Now, once we finish the impulse noise, we're looking at the Gaussian noise. Yes? If you do the median filter, actually, you will not affect the boundary if you use the cross one in the 2D case. Yeah, you just consider using the cross one. If you use the 3x3 window one, you will affect the boundary. Right, it's an observation. So yeah, so usually people don't like the square window when you do the median filter. people prefer the cross one. And the reason is just that example show you, you can preserve the corner point better. Okay, so that's basically when you do the 2D medium filter. That's the way. Okay, so there are some kind of other things like minimax or whatever. A lot of discussion on that in the book. There are some extensions and small things here there, but I'm not going to spend too much time on that. Again, I feel it's very hard to generalize. Many things is just ad hoc. Okay, so I need to tell you something, but I'm not going to spend a lot of time tell you ad hoc thing. I have the deeper thing to explain to you. So Gaussian noise. So we have some kind of, say, the representation. Suppose we have an image. We can write it as like, output is Y, and input is X, and we put out plus noise. So this is the input clean images. Okay. Now I say clean images. This is noise. And this noise, and this is the noisy images. And this you can view is like a 2D array. So Y is a 2D array. X also 2D array, and plus noise array. And pixels and so on. Okay. But this noise array, basically there is an element like a noise at the point ij, ith row, and jth column. And this is come from, follow is a Gaussian distribution. So it's a random variable. It's a random variable which say mean 0, and the standard deviation is sigma. So it's a Gaussian random variable. It's a Gaussian random variable with a mean 0 and the standard deviation is sigma. So it's come from this Gaussian distributions. So it means most likely to be 0, right? But it follows some kind of shape, the decay, according to this sigma standard deviation. So and usually we assume they are independent. So each noise point, noise pixel, they are independent. So each one is independent, and you generate independently through the Gaussian distributions and get the noise array. The noise image or noise array. Noise image plus a clean image give you the noisy images. So this is noise image. So the question is, when you see Y, so given Y, how to find X? So this is a very deep subject. You can start from heuristic way, again, very ad hoc, but then you can have more deeper subject. So image denoising actually is the subject for, in this part of Gaussian noise, not the impulse noise. Impulse noise is very hard to write any deep paper. At least we are not good enough, okay, to do that. Or most researcher cannot do much. But turn out the Gaussian noise case, if you have Gaussian noise, you add something like Gaussian noise, this kind of case, how you get Y and find the X. There are many good papers on this subject, and and better performance. And sometimes it's really too good to be true. But anyway, it's true. Okay, so it really has a lot of. It's a long history. So there's a long history in this denoising. Yes. The Gaussian is the common case, which is sort of when you do the image capturing. The noise, most cases, when you do the capturing, is a Gaussian noise. So that's in the acquisition. When you do the image acquisition, you tend to have the Gaussian noise. But yeah, in some other medical imaging scenarios, sometimes you get other type of noise. But unfortunately, it's mathematically much more involved. Gaussian people do very well mathematically. Okay, so there is a long history in this denoising problem. And let me first give you the very, very ad hoc solution, okay? And this solution, you cannot call it any something deep, okay? But just a very simple observation. So ad hoc idea. So the most preliminary idea is the so-called low-pass filtering. This low-pass filtering idea is based on the observation. Image, in most part, given a regular image which is pleasant to human eyes, so we can understand, we can interpret, it usually consists of a lot of smooth regions. So, okay, sometimes you have age, yeah, sometimes you have texture, but most image people like has consist a lot of smooth regions, a lot of surface, smooth regions. Okay, so the clean image X usually consists of a lot of smooth regions, smooth surfaces. Smooth regions, in terms of signal processing terms, is a low frequency, right? So you hear double E, and you know, you learn DSP, and then you know what I'm talking about. But if you never had some Fourier transform and what's the relationship with smooth and low frequency, maybe not very clear to you. But again, this is not my job to talk about relationship between the smooth and low frequency. Okay. Low frequency, usually things don't change much. Smooth also, things don't change much. So there must be a relationship. But deeper thing, you need to know Fourier analysis. So a smooth function, you do Fourier, it's a lot of low frequency. High frequency will be almost zero. Right? Okay, so then noise images. Noise image. So it's denoted by N. Basically, it's a lot of high frequency. So it's really the high frequency mountain. So it's a many high frequency components, right? So when you have noise, you see the things change fast. Some positive, some negative, or whatever. But there's certain distribution, but the things change fast. So you try to separate these two, how you can eliminate the N to get the X. So one very simple idea is, let's try to apply the low-pass filter. It means keep the low-frequency component and take out the high-frequency component. So that's a very simple idea. But of course, you pay some price. For example, H region, you have H. H is a low frequency or high frequency. H actually consider fast changes. So H should be a high frequency. But when you apply low-pass filter, you smooth the H. Just like the example we see, the step function. Step function, it's a high frequency actually. Step function, you can do Fourier analysis and see a lot of high frequency. But when you apply the low-pass filter, you make it like a ramp, smooth it. Okay, so you pay price for that. But people say, well, you know, at least this is the first level of the approximation, right? To low-pass filter, maybe I can remove some noise, and so on. So this is the low-pass filter idea, and this is discussed a lot in the textbook. So let me just give you some form of low-pass filter. So the low-pass filter you may use so there are some examples, okay? So let me give you some examples. Say, one example is called a uniform weighted Another example. So let me explain these two filters. Again, this is 3x3 window, and you look at this. Look at this example. You do image extension, so you have additional row, additional column. You're starting from this first one, so you have 3x3 here, 3x3 here, and then the center one is put here, okay? And basically you just, everyone uniform weighted. So this 3x3, everyone multiplied by 1. Okay, so multiply by 1, basically don't do anything, just add them together, right? You add them together and divide by 9, and write into the output images. Right here. So this is input, this output. And basically this location and this location, this is the center location. And you just add the 9 points, including itself and A neighbors, 9 points. Weighting is 1, 1, 1, equal weighted. Add them together, divide by 9, and then write it here. And that's the low pass filter. Then you move to the next locations, center here, and 3x3 is here. And again, add all them together, divide by 9, and write down the second location. And so on. And you just move on, move on, move on, and you can write the full output image file. Is that clear? If we switch the next one basically is not equally weighted. I give you more weight to the center and give less weight to the 4 nearest neighbor, and then this even a smaller weight to the 4 corner neighbor. This we usually call the side. This is called the side neighbor, and this is called the corner. And this is center. So center has 4 sides, east, north, west, south, 4 sides, and 4 corners. So like northeast, northwest, and so on. And give them different weighting. So the center weight 4, and the 4 side weighted by 2, and the other weighted by 1. So you just use this times its pixel value, and add them together, and divide by 16. 16 is, you add them together, 16, so divide by 16. And the final output, right in the center location of the output image. And the center location move. Each time, 1 pixel at a time. Once you want a pixel, and then once you finish, go to the next pixel, and so on. And one common mistake students do is they put the image input and output the same file. Then you destroy the input. So don't do that. You have 2 files. One is the image file, only read. Don't write on that. Write another file. Okay, so one image you just scan and read. And when you have output, don't replace the center. Write another place, but the same location. Just write another file. Is that clear? Yes? Centers, what's your question? The second part? Right, H1? Oh, there's no T. Here, just a low-pass filter. There's no T. You're just adding them together and write. And that output image is low-pass filtered image. You don't need a T. The T is for the outlier detection. And so if you don't detect it less than T, you do nothing. You just copy it. So the previous case, so don't mix the two. The previous case is if it's less than T, you don't do anything. You just copy the input X to the output X. Just copy it. But if you detect greater than T, then don't copy. Replace by this. That's the previous case. So there are 2 cases. One less than or equal to T, you copy the center X to the output, the location, the center location. But if not, then we replace. Okay. But this low-pass filter, you just, whenever you have the center, you're averaging with certain weight, and once you get the output, averaging output, and write on the output image. And the location is where the window center it is. That's the output center, output location. Yes? The H1 is low-pass filter. Yeah, you can do so-called two-dimensional Fourier analysis to find that. Have you taken the 483? Yeah, so this is like a two-dimensional filter. So you can assume the input is exponential, I, usually it's I omega t, right? But you can consider it's I omega 1 x plus I omega y or omega 2 and y. And then consider the filter, this is like a coefficient. And then you can find the transfer function. And then you can plot the transfer function. Then it will look like a low-pass filter. But whenever you try to average something is low-pass means when something low frequency, don't change much. You're averaging, you don't change that curve much. But when you have high frequency, you change a lot. You're averaging, you cancel the plus and minus. So you filter out the high frequency. Intuitively speaking. Can you follow me? Yeah, that's a 1D to 2D generalization. Any question about this? Okay, so this is what I want to say about the ad hoc rule. And so now we will go to something deeper, okay? But before we go to something deeper, so there are, I will say there are a lot of new development. And so I want to tell a little bit about the history. So 1998, there is a paper by ICCV. ICCV is the International Conference on Computer Vision. And there are a professor from Stanford and also Apple computer engineer, Apple engineer. They have developed an idea called bilateral filtering. So there is one thing in the paper. I will, you can find from the USC the website, but the reference in the homework number 1. Okay, I think maybe it's easier just ask a TA to upload the file so that you can access. I think it's okay because USC is covered by entire USC community is covered by IEEE Explorer. So it means all the USC students can access IEEE Explorer. And we just get from IEEE Explorer. So as long as you're a USC student, and of course you are, then it's okay. So we'll just upload the file into our DEN website. So there's the ICCV, International Conference on Computer Vision, it's called bilateral filtering. Then there's the 205. It's a conference called CVPR, Computer Vision and Pattern Recognition. So they developed another method called non-local mean method, NLM, non-local. And then more recent, there is another paper, I think 207, hopefully. It's a transaction image processing. There's a BM3D, like block matching 3D, block matching 3-dimensional collaborative filtering. Okay, so these are the several very famous work about image denoising. And actually, there are more recent papers using also sparse representation. Okay, so I don't have the paper with me, but it's using the sparse representation to do the denoising. Using the sparse representation to do the image denoising. So these are really the state of the art denoising algorithms. Okay, so I'm going to go over a PowerPoint, talk about this. And once we understand this, this actually, it's relatively easy. This can be viewed as really a very special case of this in some form. So try to understand non-local mean. Actually, it's important. And I have students work on this before. And so student had a PowerPoint, and so we will go over that, okay? So we'll look at the computer screen. So operator, can you show the computer screen? And there are some interesting history as well. And maybe we can turn off the light. Some students control the light. Because there are some images we are going to see. I think, yeah. So can we try to turn off the light? In the front row, at least. Front row, okay. Is that better? Okay. So here I want to show you how good we can get, okay? The left side, this is called the linear images. These linear images, very famous images. Okay? And because the early days, there are not many digital images available for people to process. And linear image is one of them, very early images, and beautiful lady and so on. So people love to use this image as a test image, and so it becomes so famous. These days, digital images are everywhere. So it's very hard to find one dominating image attract so many attention. But early days, most people only have photos, but they don't have digital images. So you need to buy scanner to scan images. But early days, like I'm talking about 40 years ago, the scanner is very expensive. Scanner is like several thousand US dollars. Today, scanner is less than, say, 100 US dollars, right? Scanner you can buy maybe $50. But those days, several $1,000s to buy a scanner. So people don't have scanner, and USC had a scanner, so USC can scan some images and then distribute and so on. So this is the noisy images, what I'm talking about, very noisy images and so on. But this is the algorithm we developed. This is a non-local mean, but we put the A here. A means adaptive. So the student had the thesis chapter on this adaptive non-local mean, and we are able to get this kind of result. And you can see all the noise hyperlink been removed, while the edge been preserved very, very well. No blurring in the edge. Texture preserved very well. So it's like a marvelous result, right? So you can get so good result after denoising from here to here. Okay? So I will tell you how to get that. And a little bit about denoising. Okay, so early days, it's analog images. So there's a TV, and you can try to handle the analog images. And there's some denoising, but it's really about the analog signal processing and so on. So we don't talk about that. Too early days. The first digital image is in 1957. Okay, 1957. That's the time when I was born. So the first digital image is the same as my age. So you can see how long it is, okay? You get the first digital images. And what's that? It's this one. Okay? And this one is a very small image. It's 176 pixel by 176 row and column. So very small. And this guy, this is the father, and this is the son. Okay? So he has a 3-month-old baby, and he took a shot of his son and then scanned. So he designed a scanner, scanned that image, and that's the first digital images. Okay, grade level images and so on. And this you can find from the YouTube. Okay, let me see whether I can get that. Yeah, this is a YouTube video you can play, and his son came to see, after explain, and his son show up. That is, it's adult already, like maybe year 40 or something. So that video is interesting. There's a later part, the son show up, but it's an adult. Okay, so 1970s, USC, sort of the very early days, it set the Image Processing Institute. so-called IPI, and that's the first institute. Then we put a signal, and so later on become signal image processing institute. In the beginning called IPI, and later on put SIPI. Okay. So a lot of researchers there, and Pratt was director, and at that time he started to write his book. Pratt book is that, and so we'll stick to that because in memory his contribution to in the image processing. So that's one of the early national, I would say, national funded big project in the image processing. But these days the U.S. government does not want to fund the image processing research anymore because the commercial sectors like Microsoft, the Google and so on, the commercial company has a lot of activity in image video processing. Then why government should fund? Government funding in U.S. government funding is funding something for the future. Still, the industry is still not yet developed, like nanotechnology, like something more advanced, more future, and the government invests money on that. But once the industry pick up, then government look at next stage. You know what I mean? So next government funding and industry funding is complementary. So now multimedia is all industry funding, so the government does not want to fund. So like, for example, my research group, we do a lot of multimedia. We all get funding from industry. We don't get money from the government because there's no money. Government does not want to do this. Computer graphics, the same thing. Government doesn't want to fund the computer graphics. It doesn't want to fund the computer network. All this kind of field is so mature. Government does not need to invest. Okay? But it's an industry. But good thing is, if you are working in this field, there is a big market for you to join. Right? But some field is very early. One is nano is still early, so you need to find more like spatial lab. Bio is sometimes, depending on which bio. Biomedical imaging is very mature. But if you talk about bioinformatics, then that's very early stage. So the government invests a lot of money for the bioinformatics, brain science, brain understand human brain, and so on. Then it takes some time for the industry to pick up. So I know quite a few people specialize in bioinformatics, but when they go to the job market, they cannot find teaching position. Then what they end up with Wall Street, because the Wall Street they use statistics. There's statistics training because there is no bioinformatics in industry. Right? Some drug companies need a little bit of researcher, but very few. So there is no commercial company can absorb the talent. So they need to go to Wall Street doing all the financial analysis and so on by switching field. Okay. So image processing in that day, 70s, it's very early, government funding, and industry still not yet. There's no digital camera, there are very few scanners. So USA is leading in that, so it's more than 40 years. Last year, we celebrate the 40th anniversary of the Signal Image Processing Institute. So that's 72, now until so 1972, we started IPI. And so this is something hidden, okay? We're not allowed to show, okay? So Lina Images, okay, this is a Sweden name. It's a model at that time. Now she's like, I would say, 60-something, right? 40 years ago, it's 20-something. Now it's 60-something. Still beautiful lady, but it's still a certain age. So in Sweden, a Swedish model, and there is a Playboy November issue, 1972. Okay, that's the time, the city. And Professor Sandy Sobchak, at that time, she was a young assistant professor. So he looked at the very colorful Playboy magazine, and then she take some image and scan the color image. But he only scanned the head part. He didn't scan the whole thing. Okay. But anyway, I don't know who found this Miss November, right? So scanned everything. But okay, and so that time is IPI 72, but later on we add CCP. Reason is tired of the usual test images. In those old days, images are remote sensing images. Space is the image taken from the airplane, look at the ground, look at like a forest or different kind of fields, different kind of city, rural, urban areas. Very boring, black and white, and no one really cares. Suddenly we have the this kind of human subject and the good dynamic range, colorful images, and so on. Okay. So that's about the linear image source, and so we only get this part. Okay, now about the digital image noising. So there is some early work by PEMI, Pattern Analysis Machine Intelligence. So Professor J. Slim, that's an MIT professor, so he published something in 1980. Okay? But this is a very early work. Later on, whenever you have new tools, there is a denoising application. Okay, so like people develop wavelet, so they're using wavelet to do the image denoising. Winner filter and total variation minimization, all kinds of things also can be applied to denoising. Denoising is like the #1 problem for you to test. You show, okay, my technique can be applied to image processing. Show in image denoising. That's the easiest problem. Then you can do so Gaussian scalar mixtures and so on. And of course, bilateral filtering is also another case. Then 2005, there's a non-local mean algorithm developed. And this is like a result, the Gaussian scalar mixture. From here to here, but you sacrifice something, right? The blur, the edge, blur, and so it's not very good. Okay, but this one seems can handle all this kind sharp edge very well. So mathematical formulation. Okay, so image denoising is a classical problem. So you have the output here, using X to show the noisy images. S is original, N is noise, and non-local mean is here. Right now it's much more. I think it's 600 or something. This is early days. Okay, so let me explain this concept. Okay, so what we can do. Okay, the intuitive idea. Suppose I have N observations, so X1 to Xn. So we have original source signal, source images, plus different kind of noise images. But this noise image, N1, N2, Nn, are not correlated. They generate independently. Okay? Actually, the noise at each pixel also generate independently. But this N1, N2, N3 are also noise images, but they are independent, generally independent. So I can create N noise images. So it's a source plus different noise images, N of them. Then if I have generate all of them, if I am able to observe them and add them together and find the mean, then what will happen? You have two parts, right? Source part and noisy part. Source part is S plus S for N times. Divided by N is S itself, recovered. Noise, N1 to plus Nn divided by N, then you get this one. And this one, if the mean still 0, right? Because each one mean is 0, so you add them, divide by N is 0. But how about the variance? The variance actually become much smaller, okay? It's a variance basis like divided by N squared. So variance is much smaller. So that means you really very constant. When you adding all this noise image together and have N copy of them, each pixel has N copy now. Each location you have N copy, right? You have small N copy. You add all them together along the different samples, add them together. So the noise really, the mean is 0 and the very standard deviation is very small, means they are very constant along the 0. There will be no large deviation, standard anymore. Okay. So, let me draw the diagram. Operator, can you show the image pad? And then we can have a break. Okay, let me just draw this first. So suppose you have a Gaussian distribution, says 0 mean. So suppose this is mean is 0, sigma is still sigma. Okay. But if you consider the averaging of this noisy images, okay, and then the statistics will become the mean still 0, but sigma now is I think it's n divided by, this is nu, right? This is say prime. So the mu prime, after this one come here, then the mean still 0, center at 0, but the standard deviation will shrink by a factor of n. The variance is shrink by n squared, but standard deviation will shrink by the n. Sorry, this is small n. Because it's small n, right? So it is shrink, so means the standard deviation will narrow. So most noise will be very concentrated in the 0, much more concentrated in the 0. In the before, the noise can be big range, but after you do the averaging, the noise range become narrower and narrower. So something like that. Okay, and let's come back to the PowerPoint. Let me show you the final one. Operator, can you show that? So this is some examples. Suppose you have the one sample like that. You're adding this 10 samples, N1 to N10, get that. You get N1 to N100, and add them together, get that. Okay, so suppose you have 100 observations, and add them together, divide by 100. This is something you get. The noise disappears. Noise take a mean 0, and then the noise, the variation becomes smaller and smaller. Really, noise cannot contribute much. There's some positive noise, there's some negative noise. When you add them together, they cancel each out, right? So that's one idea about this. And based on this, how we get non-local? Basically, how you get 100 observations? It's impossible, right? How you get 100? You only to observe once. That's all. But you can find small patch and search in the image whether you can find similar patterns. So that's where non-local comes from. Okay, let's stop. Let's have a break for 10 minutes. Let's turn on the light.
Can I ask a question from earlier in the lecture about the digital filtering, the digital interpretation? So what kind of filtering were you doing? What kind of processing were you doing? Can you maybe go back to
You talk about non-local mean, or you talk about histogram polarization?
Oh, I'm talking about like histogram. Yeah.
That's no processing. Just do the mapping.
Oh, okay. I'm confused then why it looks.
No, do the mapping. You don't need to do any processing.
I think that's why.
Okay, so let's resume. Let's turn off the light again, the front light. Okay. So now we try to avoid averaging multiple observations. Okay, we do not have multiple observations. What I'm going to do? So suppose we have one image. But let me give you a very special example. Is we have some kind of gift wrap-up paper. So we want to give someone gift. We can have some paper to wrap the gift, right? So this is one example. It's a USC logo there as a wrap paper for the gift, right? So you buy something from USC store and you can get this. Then why I show this case? I want to show this special case. It means there are some pattern, signal pattern repeated in one image, right? So USC, you repeat it. So if you cannot observe multiple times, maybe you are able to observe from the same image similar pattern, right? So suppose there's USC 3 times, and you can consider the noise independent, but signal is dependent. Signal is identical, actually. So you add them together, you still can get the same effect talking about. And this is non-local in the sense, this signal repeated, but non-local. Not like a smooth region, you have to look at local. This maybe you can jump around, jump a distance and find the identical pattern. Right? You jump a distance, so you call non-local. That means so this USC is non-local, but they are identical signals. So this is called the repetitive patterns. Then we can follow the same idea, right? And this student is smart. He used all this kind of very good example, so motivate you. I think a lot of image processing video. And sometimes I needed the help, TA's help is prepare a lot of pictures. But TA is also very busy, so sometimes I don't want to bother them that much. But sometimes I have students working on similar subject, and they have beautiful PowerPoint, and I borrow them. So this is really beautiful pictures. So he used this gift paper to show the repetitive idea, and then the same idea can generalize for this single image, but the multiple contents. Okay. So now let's go a little bit. Say, Professor Guo, I cannot develop a method just for the wrap paper, right? I want something more general. So if there is no identical signal, what can I do? I say, well, you look at this, images, but you still have something sort of similar. Say, along this line, you look at the pixels. This pixel has very similar distribution, means the right-hand side is green, the left-hand side is red. So these pixels have similar flavor, and this has a similar flavor, and similar here. So can I find similar patterns, but not a big pattern, but smaller pattern, a small window, but their local information is very similar. And can I add them together? Okay, so that's generalized self-similarities. So now this is the mathematical framework. Okay. So this point is pixel I, location I, pixel I, and this is pixel J. I and J right now is two-dimensional index. Even though I write I, but imagine this is I is I1, I2. Okay, sometimes you use I, but I is a vector. So I is the I1, I2, J is the J1, J2. But I don't want to write so many IJ. So just I is a two-dimensional index, J is a two-dimensional index. So this is just a pixel. This is also a pixel. Pixel value. So in order to reconstruct the Fi, so put a head. Head means reconstruct the value. Fi is the original value, but head is the reconstruction value. So the noise value, reconstruct value, is equal a certain weight times Fj. Okay, so Fj means some pixels, but I'm looking at given them certain weight. And how to get this Fj? Okay, C, don't worry. C just a normalization. So we try to normalize this so that the weight will be eventually add all the weight equal 1. Okay, so Ci just a normalization factor. Wij is the weight. This weight relates to these two index, I and J. J is from a local search window. A spatial case, omega s is whole images, but the complexity is too high. So you want search similar pattern over the whole image too high. So you usually limit the search range in the local neighborhood of pixel I. So there's the pixel I you want to denoise. You look at some certain neighborhood surrounding I. Okay, this neighborhood size usually say maybe 30 by 30, 31 by 31. These are typical order. Okay, so you search. So there are 900 points you have to search. So you look at the J in the local window of the I, center at I, and then you give a weighting. And this weighting is determined by the relationship of this I and J. And what's this two? This weighting coefficient determined by the similarity of the Gaussian neighborhood between the pixel I and J, and using this as the expression. So Ni is the neighbor of the I, Nj is the neighbor of the J, and I want these two neighborhood has a sort of small values, and this small value, using this is like a Gaussian distribution. So this small value, if the smaller, say, if these two neighbors are identical, you get a 0, right? You get 0, so the weighting coefficient will be 1. But if these two very different, so Ni minus Nj, the neighbor are very different, you get something big. So exponential minus something big, you will get what? Something very small, right? So we try to look at the neighborhood of the I and J. The neighborhood is very similar, the weighting will be high. Neighborhood is not similar, then the weighting will be low. So let me give you the previous example. So suppose let's consider this is something I is the location, pixel I want to denoise. I can search a certain window, the 31 by 31, say for example, so 900 points. So I go over all the points and see which pixel has a very similar neighborhood. So suppose I go to this one. This one surrounded by green, and this one is half green, half red. Will be this similar neighborhood? No, right? And how large is the window? N. Usually it's around, say, 13 by 13 or 11 by 11. Okay, so window is not too big, and you search like 31 by 31. So you look at 11 by 11 and 11, and these two are very different. So all these are very different, except only something will be similar is what? Pixel along this line. Agree? It's only pixel along this line will be similar to me. All the other will not be similar to me. Okay, so means all the pixel here, I will give more weight. And the other, I will give very small weight, almost 0. Okay, so that's basically the idea here. If you look at this one, say this one, this point, okay. I look at the 30 by 31 window. So I look at all the neighbors. All these neighbors are very similar to me because they all look at 13 by 13 or 11 by 11 window. They are all very similar to me because they're all red. So then I can equally weight. So eventually you have weight, right? Weight about the same, and then you normalize. So it's equally weighted. So this guy, you can search the neighbors. And this guy, you can also search the neighbors. So everything you can search the neighbors, right? And then you take the shape into consideration, right? There is a shape, because the shape determines the neighbor look like. If there is an edge, you will tend to search the point along the edge, give the weight for that. If non-edge, you will search the non-edge group. And you know why we want to do that? Because if we try to add in all this patch surrounding that, we still can keep this edge. Because the signal is a green, red with some line. So you're adding this patch together, adding this kind of noisy pixel together. Actually, you are adding the pixel, give the pixel some, but you're adding them together, you can preserve this kind of the shape. So you're really doing the denoise for that one as well. Because this kind of pixel, we basically, they belong to the same group. They belong to the same group. So we can say we use this one, the neighborhood, to determine the IJ category. So the same neighborhood, we can say the AIJ is sort of closer in property. If the neighborhood is not similar, we can say IJ are really not similar. And when they are not similar, we should not let them participate in a big role in the denoising. Okay, so denoising, you try to find a weight, and this weight, you will look at this Fi, Fj, and Fi, if they have similar neighborhood. If they don't have similar neighborhood, then we will put this weight to be very small because this will be big. And this 2A is really about the Gaussian shape. Okay, so it's weighted by the Gaussian kernel. Let me see whether I can find. Can we turn on the light? Turn on the light. So what's the particular form talk about? So say you have a point I, and then there's a neighborhood of I, and then there is a point J, and there's a neighborhood of J, and you subtract them, right? You subtract them. So basically, you subtract one by one. Each pixel subtract the difference, right? But so pixel-wise subtraction. So Ni subtract Nj means a pixel-wise subtraction. So this one subtract this one, this pixel subtract this pixel, and so on. Okay, so you subtract one by one, and so on. And this one, actually, I give a weighting of the Gaussian shape. So it means it's a circular shape that I give more weight to the center. And then the Gaussian shape, I give the smaller weight when they go outside. So I try to also consider the distance effect. So the neighborhood similarity, I say, well, I emphasize the similarity in the center. If you live far away, I allow some variation. So if you are more similar in the center, and even some dissimilarity outside, it's okay. So there's a weighting effect for that. So that's explain these terms. A is just like sigma. It's a Gaussian distribution. Okay. So let me write down this. Let me see whether I have a formula for that. So, sorry. So GA, let me write down this. The filter shape is a Gaussian one, and the K, say K1, K2, it's really the window shape, okay? So this is equal A squared. A play a role like standard deviation. And K1, K2 is here. The center is 0. And this is just like a pixel distance, right? So this is like a K1, K2, K1, K2. And this K1, K2 is a two-dimensional index. And really, it's the after you subtraction, these two, and the center and the center. The center and center here, you consider 0, 0. Okay? And then give the coordinates K1, K2. So this is the weighting function you have. So once you have this subtraction, you multiply this weighting. Okay? So it means you emphasize the similarity in the center, and the similarity you can sort of make it smaller. It doesn't matter. So still look at the similarity in the close to the center region. Okay? And let me see what else I want to tell. There is also some related to the H parameters. And H parameter, there is a certain way to choose it. I think I remember it's like close to 20 or something. It's empirically decided there is a certain value of h. Okay, yeah, I couldn't find that. Anyway, you can go to see the book and or see the paper and so on. Let me finish this. Okay. Any question about this? So basically, you have the two neighborhoods. You subtract them and weight it by the Gaussian, weighted by the Gaussian function, and then using that to determine the corresponding weight. So this one you have to do for every pixel. So if I is a pixel-based reconstruct value, you go and then there is the omega s surrounding I, and then you search the surrounding pixels, and each one calculates weight. And if your weight is too small, you can just set it 0, right? And then you move around and so on, and then scan all the images. Scan all it pixel by pixel, and you can get a local mean. Okay, can we turn off the light? Let's continue the PowerPoint. So there is some adaptive we can do. So we can adjust the denoising parameter like h, like omega s size, the local search window size, those kind of things, okay? And so these are the generalization. You don't have to worry, but I just tell you things can be done with different things. Let me see. We can try to look at the different kind of the edge point. Let me just scan through that quickly. Basically, the one idea is try to choose how large the local neighborhood you can be. Okay, you want to choose a smaller neighborhood or larger neighborhood, and so on. So this is the n. Determine the neighborhood size. It can be flexible. Okay, so it can be flexible. For example, the center here you have shape like this. The center here you like this. And here you may want to get more points participate because it has some kind of strong directionality. But sometimes you don't have that. You know, actually, the reason you want to do this, try to look something a little bit bigger is because you don't get this kind of contributing pixel too much. There are fewer. But if you have this kind of thing, you can get many contributing pixels because they are neighborhood all very similar. So you don't need to search large. You're just using some fj, a smaller fj. You can averaging well. But along the edge, actually you search window, but a lot of fj will not contribute much because they are not similar. So you need to search a little bit longer in order to cumulatively find similar neighborhood. You know what I mean? Because along the edge, the similarity will come from this point. It will not come from the other side. So you need to make the window a bit bigger and so on, search a larger range in order to get enough to contribute to the denoising. But for this one, you 2D, you search everyone, all direction give you the good fj. This fj will be similar to you, right? So you can consider different kind of search window, omega s. Okay. So this is the way. I'm not going to go over too much. And block matching, you can also consider different kind of way to choose. It's too complicated. So there are different ways you can do. Another thing is about edge orientation. Sometimes you want to search the edge here, but sometimes the edge come here, there is a change of direction. So you may want to allow the neighborhood to rotate. So in order to increase the number of similar patch. So sometimes the neighborhood rotate. You want to be able to rotate the neighborhood so that you can get more fj, which can be adding which can add the smoothing. So let me just show you some denoising comparison visually. So there's using the low pass filter, and this is like a weighted low pass filter. This is equally weighted. This is Gaussian weighted. So these two are all low pass filter. And you can use a partial differential equation approach to do the denoising. You can do total variation, you do non-local mean, and then it's our work, adaptive non-local mean. And these are the 7 representative images. And you can see the result. The non-local mean, you get this PSNR, and adaptive non-local mean is 31. So the improvement in PSNR is bigger. So these are the different kind of sigma, different kind of standard deviation, and then it's always get better result if you do adaptive. So these are the different methods, and different sigma, different color is different sigma, and different method. You can see the noisy image, the PSNR is the lowest, the quality is the lowest, and the low pass filter is here. The PD or total variation, sometimes you don't improve much in the PSNR. Okay. Visually, you're better, but calculate PSNR does not help you much. But our method can improve both the PSNR, also visual performance. So now let me show you the noisy image, sigma equal 40. The median filter, do you like this? Low pass filter, right? But low pass filter will not give you the very sharp images. The Gaussian, still not sharp. Partial differential equation, still not very sharp. Total variation is sharper, but still noise. You cannot handle the noise. Okay, surface noise still not. Low non-local mean, it's sharper, but of course, it's still some kind of a smooth surface. How about this? Adaptive non-local mean, right? So this again, noisy images, non-local mean, adaptive non-local mean. I think the girl will like this image more than this one. Similarly, non-local and adaptive non-local. So there are some medical imaging, and it's related to some other type of noising, like racial noise. So, yeah, okay, I'm not going to go over that. So let's come back to the homework. Okay, we'll see how much we can do now. Okay, can we turn on the light? Okay, so we're starting from this mixed noise in color images. So basic one. So in this part, you will perform noise removal on a color image correct by mixed type of noise. Mixed type, I think it's all kinds of noise, right? So you have the saturate noise and the dark, the black one. Can you see the black one? Do you want to see a bigger one? So you see some black dots, that's a 0, right? And you see some yellow dot, right? So yellow dot and blue dot and all kinds of different blue dot or all kinds of things. And there are some kind of also a little bit like Gaussian noise. So anyway, this noise is crazy, okay? So you have many things. Okay, so you have to identify how many noise in these images. Okay, so this is called the noisy paper images. So number one, please identify noise type in the image. Answer the following question. Do all channels have the same noise type? So you have RGB 3 channels, so you tap them out. red channel, green channel, and blue channel, and see what noise is inside. So each one become like grade level images, right? Just purely one color, R, G, or B. And take a look at separately and study what noise inside. And then you have to explain what's inside. B, should you perform filtering on individual channel separately or both noise type, for both noise type? So it means, should you handle each channel separately? And for both noise type. Both noise type basically there are two noise types. One is the impulse noise, one is the additive noise. So it gives you the hint already, right? So anyway, there are two noise types and so on. And you try to handle them separately. And C, what filter will you use to remove the mixed noise? Okay. So say you have to do the impulse noise removal, right? And then you have to do the other denoising method. Can you say these two filters in any order? Justify your answer. So suppose you want to do low pass filter and then the impulse noise removal, or you want to do impulse noise removal and then low pass filter. Which one? Well, the order matters. So you have to think about. Okay. Well, the order matters. If you do one thing at the first, do the thing other, or you switch, will that be the same? And please discuss the effect of different filter window size. Okay, so you can discuss that. You try different window size. First you try it, and then you can explain why. Okay. Number 2, try to get the best result in removing mixed noise. Describe your method and discuss the shortcomings. You may not be able to do a perfect job. So if you still fail something, you discuss why you fail. So give some suggestion to improve its performance. So you can do something as to your best effort. But if you still cannot, you can talk about just in words, right? In English, okay? So there may be other way to improve it. There's no implement, but explain them along with your motivation. You can use suitable plot images to support your arguments. Okay, so this is about this particular case, basic. Bilateral filtering. Okay, so bilateral filtering, there is the reference 1. So that's, as I said, 1998 ICCV paper by Stanford professor and Apple engineer. So in most low-pass filter, we often see degradation of edges because you do low-pass filtering. You smooth the high frequency. However, using some nonlinear filter, we can preserve the edge. Bilateral filters, one such kind of filters. And bilateral filter, you can write down this, integral form. But let's forget that. Let's look at the discrete form, because I think we can look at this discrete form. So again, X and the Kc, these are two image pixels. So if you want to find X, it's the one pixel. You can view it as X1, X2. Okay, it's a 2D index, X1, X2. H is the value after reconstruction. It's this normalization factor. Okay, K, so don't worry about it. Just to try to make everything, the coefficient sum will be 1. So there is the pixel value at Kc. So this is just like a J in previous case. So these are the pixel value at the Kc, and Kc is within a search window. So there is the X you want to denoise. There's a point X you want to denoise. You look at a local window. Okay, you look at local window, and how large you want to choose. I think it probably is in the paper, but anyway, I think you can look at a certain degree. You don't need to go far. Okay, you need to go far because there's things control these two terms. So yeah, you need to add the grade level of the surrounding pixels with some weight. So there are two ways to do the weighting. So these are the weighting, okay? And weighting determined by the Kc and X, okay? So this weighting form is not using the local neighborhood. This weighting form uses two things. One is the spatial domain distance. Another is the C is the spatial closeness. How close these 2 points? So X is the point you want to denote, and you look at the distance. If they are closer, you give a bigger weight. If they are far away, I give a smaller weight. Okay, so these are the two, and so the C, X, C, and X is in this form. This is about the distance. So you look at the Euclidean distance. So these are the x1, x2. This is C1, C2. You look at the distance. So basically, you try to consider a Gaussian shape. You're closer, I give a bigger weight. Far away, I give smaller weight. Okay? So this is about the C. C is formed this way. And this is sort of the spatial effect. Then there is the so-called spectral effect. Spectral effect means what? Pixel intensity effect. So this S is a spectral effect, pixel intensity effect, or called the photometric similarity. So it means the two gray label, are they close or they are not too close? If they are close, it means they have, say, they all say 200 gray label. They are very close. But one is 200, one is 100. Then the gray label change is big. You know what I mean? So I want to see these two pixels, the gray label distance, in terms of gray label distance. The gray label distance is very close or gray label very different. So this is their gray label. And S means the gray label distance. And the distance, again, we use this. So we look at the gray label difference and then look at the Gaussian weighting of the difference. So that's the weighting for this term. So the weighting for this term and the weighting for this term is here. And then you multiply this together. It's called bilateral. Bi means two, right? Bilateral. So this is one factor, spatial factor. This is a gray label distance factor. So these two combined together as a way to weight this efficacy. So it means I will give the best weight is the distance is close to me, just my neighbor. And this one, they have the same gray label to give you the biggest weight, right? Or something far away, then I will decrease the weight, or something gray label is different from my center, then I will decrease the weight. Okay, so these are the weight, so-called bilateral weighting, and this is bilateral weighting, and this is C. So it's a one by one pixels given different weight, and you add them together. And how far you should go? You can look at the distance. Sometimes there is some distance, just the term already very small. It doesn't matter here, you know what I mean? Because this term, once you go a certain distance away, it's already almost zero. So then you don't need to worry about that. Okay, so you can look at this function, how fast it decay. How fast it decay, then you can search to a distance. Say, if this term less than 1%, then you can just assume, you don't have to search other things less than 1%, because the weighting is only 1% already. It's too small. Okay. So this is called bilateral weighting. So A square, where is A square? This is for the non-local mean, I think. There's no A square anyway in this. Okay, so then the K is what? K just adding all this weight together. So K is a normalization factor. Okay, so you have all the weight, right? Different weight surrounding, and you add them together, it's just called a K. So K over 1 over K, just the normalization. So omega x, the final window center around x, and so on. So these are spread parameters. So implement the bilateral filter applied to the Lena as shown in figure 10, this one. Explain the role of C and S. Okay, you can choose C and S. This is the sigma C and sigma S. So here, C and S is here. Okay, these are spatial closeness and spectral closeness. And discuss the changing filter with respect to the value of sigma C, sigma S, and the window side. So does this filter perform better than the linear filter implement problem 3A? Actually, according to history, of course, the low-pass filter is the worst. Then bilateral filter is better than low-pass filter. But non-local mean is 7 years after, so definitely be better. Okay. Non-local mean try to consider the local neighborhood, not only just consider the location and not only consider the grade level difference. It really consider local neighborhood match. So this is non-local mean and so on. So this is advanced. So any question about this too? So this is both are considered advanced or no? So bilateral is considered basic, and non-local mean is advanced. And then finally there is a BM3D, and BM3D I will let the TA to go over that. Okay, but let me talk a little bit about the bonus. Okay, so you already have 100 points up to this point. Okay, you already have 100. So this 10 additional. So if you feel you can do very well in your midterm exams, you don't have to worry about this. Okay, but you feel you may not do well in the midterm, then you may want to do this. As I explained, what we'll do is all the students, if above 100 in the final, okay, in the final scores, including everything, above 100, you all get an A, no problem about that. So then I only do the curving for something less than 100. So all the students less than 100, there's a group. I try to do the curve, means about 50%, 50%. 50% is A, 50% is B. And of course, there are some outliers always, right? Sometimes it's very, very bad. I cannot even give you a B. I need to give you a C. Then that will happen sometime. But the most curve. So it means if you're above 100, then of course you are in the safe group. But if you're not in above 100, you still, curve based on that. So you are not getting penalized. But if you look at the whole class, actually we have more A than B. You know what I mean? Because there are students above 100. So you will not penalize by not doing the bonus point. Okay? So let's look at this BM3D. Okay, in this one, you're familiar with the state-of-art filtering method proposed in 3. This is 2007. Please explain BM3 algorithm in your own words. Okay, so you need to understand this one and explain that and implement a BM3D filter. Write your own code or use any available online source code, but include the source in the reference. How kind this is. Actually, there is online source code. Okay, so you can use that. This time is okay. Okay, this time is okay. To denoise the linear, okay, actually it's recommended I use the code provided by also on their website 4. Their code is written in MATLAB, so it's okay to use MATLAB for this part. Even if you have been coding on the C++ platform, you will still qualify the 5% bonus point if you have used Sigma everywhere else. Okay. So it means the source part, you use the author code, MATLAB. The other part you use C. You still can get a 5% bonus. Okay? Because everyone we talk about, if you use C, you get a 5% bonus. Right? So this is like double bonus. 10% is already bonus. You get another 5%, so double bonus. Okay, so this course is very good in the sense, I argue to work very hard, but I give you a lot of bonus opportunities. So you can collect bonus here and there along the way. So many bonus. I play the game, right? A lot of bonus. You hit this, get a bonus. Hit that, get a bonus. I hope you enjoy the bonus points. Right? Design effect of several tunable parameters on this denoising result. Both NLM and bilateral R spatial domain filters. Okay. Actually, this is using some spectral information. Would you classify BM3D spatial domain, frequency domain, or both? Justify your answers. Conduct qualitative performance comparison between these 3. So there's some test case, you use 3 methods, BM3D, and non-local mean, and the bilateral, and then discuss. Okay. So, I hope the TA can spend some time talking about BM3D during the discussion. But actually, this is the bonus. So if the TA does not want to do it, it's also fine. Okay. I will discuss with them whether they want to say it. But because this is an additional thing. Any questions about this? Okay, so if you don't have any further questions, we will talk about one small subject. And so to finish this image enhancement. You know, after all this material, actually you really have a state-of-the-art image processing. You go out anywhere, you talk about PM3D, non-local mean, you will get a lot of respect when you do the interview and so on. Believe me, this is usually not in the very typical image processing class. This is like a very advanced, research topic or whatever. But here, I really care about your market value. That's really the thing. As a professor, I think the most thing the professor feels satisfied is you get a good job from good companies. So I always keep that in my mind. That's a key issue to me. Okay. I really care less about A or B or those kind of things. I mean, the important thing you get job from, say, Apple or Google, right, or Qualcomm or whatever, Microsoft. You get job from all those top companies, and very, very happy. That's really my service here is to make you valuable. Okay. So yeah, don't hate me if you do very heavy homework. Okay. I'm really trying all of very good, intention, not make your life very miserable. But without this kind of practice, how can you be better? How can you, outperform other candidates? Right? There are a lot of good universities, right? And their students are also good. So how you can do better than them? Because I sort of push you very hard. So that's my philosophy. Okay. So there's one more thing I want to talk. It's sort of the related to like high pass filtering, okay? But it's called edge crispening. So the idea basically says, well, if you have a photo with an accentuated edge, so mean the edge be emphasized. It's more pleasing to human eyes. So we want to see sort of strong edge, okay, the edge being emphasized. That's usually more pleasing. Okay, so the edge enhanced images, it's usually you feel better. So how we do this? Edge enhancement, edge enhanced images. One idea is try to do the high pass filter, and the reason for that is because edge is a sort of high frequency, right? So we may want to do the idea. Number one is a high pass filter. But this high-pass filter idea is not a good idea. Okay? Whenever, I don't know whether you have the DSP and so on, but most professors will say, don't do high-pass filter. Do you know why? Because you amplify the noise. Yeah, you want to amplify the edge, but unfortunately you pay the price to amplify the noise. So high-pass filter is something you don't want to do. You don't want to do because you amplify the noise. So it's turned out a bad idea. Okay, bad idea. And why? Because you amplify the noise as well. So another idea, actually, it's a better idea. Suppose I want to. So we can say improved idea. So idea 2 So improved idea. So usually people don't implement the high pass filter directly. Usually people implement low pass filter and then 1 minus low pass filter. That's a better idea. You say, well, is that the same as the implement high pass filter? No, it's not the same. You know, high pass filter usually means subtraction. Subtraction, finite difference, that's a high pass filter. But usually people don't like that. But you can say it's all pass filter, subtract low pass filter. These two filters are stable. And then you find the difference between the two. You get the high pass. And that's a better idea. So basically it's like all pass, subtract low pass, then this will be sort of equivalent to high pass. But this is a better idea. Okay? Even you try to do the same thing, but this implementation is more stable. It's more stable as compared you try to implement the high pass filter directly. Okay? So this is called improved idea. It's built upon the previous idea, but it's a different implementation. So all pass means 1. All pass means 1, everything go. And the low pass, subtract. So the way we implement will be look like the following. So if we have the F, so we have the images, and then we have the all pass, and we can give some scaling, and then we have also a low pass filter, and we have some F low, and then we have some kind of weighting. So there is a weighting factor. So there's weighting is C to C minus 1. So this is a weighting. And this is 1 minus C. Or you can call it scaling, right? This is just a scaling. So this is just weighting or scaling factor. And this plus, this minus. And then the output, the output is a G. So this branch is all pass. This branch is low pass. And then you consider a certain weight. Okay, just scaling or weighting this guy and this guy. And C typically is between 0.6 and say 0.8, say 0.885, something like that. So if we choose, say, let's C equal 0.8, and what will happen? So if C 0.8, the top one, C 2C minus 1 is equal 4/3. And the lower one, 1 minus C, 2C minus 1 is equal 1/3. So in other words, you amplify the whole image by 4/3. So make everyone higher, the all grade level higher. But then you subtract the low pass version by 1/3. So then that means you keep the low frequency part still the same, right? But the high frequency part, you have the 1/3, 1/4, and subtract almost nothing. Well, why? Because the high frequency will be filtered out here, right? The high frequency will not pass through. So high frequency will not pass through. So you basically have times the high frequency by 4/3. So high frequency be amplified, low frequency be canceled out. So low frequency just keep 1. High frequency become the 4/3. So that's give you the equivalent like a high pass filter effect. But you are not subtracting anything, right? So you are averaging, scaling, and subtracting here is okay. Just one by one, the image subtraction, that's okay, and get the output. And there is a called a spatial name. It's called unsharp masking. Why it called unsharp masking? Because this is unsharp. Low pass filtering is called unsharp. The whole technique called unsharp masking. Why? You try to get a whole image, but get an unsharp version and consider this a masking effect. So you have whole image, but raise the magnitude by a certain degree, but then you get a unsharp version, just a low frequency part, and then subtract that out. Then the high frequency will preserve. So the whole technique called unsharp masking. And unsharp masking is one way to enhance the edge. So you make edge look better. Okay, the edge looks sharper. So don't do the high pass filter. The high pass filter is people know it's not going to work well because the noise will be amplified. And sharp actually you can also denoise a little bit because low pass filter denoise. Okay, so actually it's a sharp masking. You can see better edge and also noise being removed in a certain degree. Okay, so that's a commonly used one. So there is one thing I want to talk before next lecture. It's next time we'll talk about edge detection. So next week we'll talk about chapter 2, edge detection. I write down here, but I'm not going to talk. Okay, so don't worry about that. So we will talk about edge detection next week. But here I want to say one thing. It's about the notation. Okay? The book and I, we use different notation. Okay? We use different notation. So there's notation difference. But I want to explain that. Okay? The book uses notation commonly used in the signal processing context. So digital signal processing, there is a concept called impulse response. How many of you have heard this impulse response? Okay, very good. Okay, almost everyone heard about impulse response. So impulse response means when my input is the impulse, right? Just means xn equal s0 is 1, and the other are zeros, right? Just one impulse at the origin, and then the other. And I observe the output. Right? But have you ever heard about the operator mask? Operator mask. Operator mask. Have you heard about this? Actually, you've seen this today, okay? You've seen this today. You know where you saw? The low pass filter one. Where is that? Sorry, let me search that. This is operator mask. Operator mask basically says, I give you sort of a mask. This is like a mask, right? I give you the weighting coefficient, and this operator mask basically says, you put the mask on the images, and these are the corresponding weighting. So you multiply the pixels. The uniform is a spatial case. Generally, it's like this. So you multiply the pixel value with different values, and you add them together, sum them together to give the output. So the output is one pixel. The input is multiple pixels. That's called operator mask. Okay? And you say, what's the big deal? Do you think that there will be some relationship between the impulse response and operator mask? Or you think that these are the two different things? What do you think? They must be related a certain way, right? They must be related a certain way. Actually, there is a group of people when they talk about the numerical computation, okay? And there is a numerical analysis. Say you do the continuous operator, for example, integration, and you want to do discrete implementation, right? The early days when computer invented, they want to use computer to do all the calculations. So differentiation, how you find the discrete form to do the differentiation, how you find the discrete form to do the integration, how you find the discrete form to do many, many things. And all that branch go to the numerical PDEs, numerical ODEs, how you do numerical ordinary differential equation. So there are a lot of people working on numerical analysis. And those people all use operator mask. They don't use impulse response. Impulse response is the signal processing people use impulse response. But honestly speaking, signal processing at the early stage you will consider a very small group. And numerical analysis is a very big group. Okay? They are much more influential than the signal processing. And one history is the signal processing early days actually is the same as speech processing. The origin of signal processing is not really in other numerical analysis because they are so weak. So the only one field that makes it very different is speech processing. So speech processing is the early day. All signal processing actually is the same as speech processing. So speech processing makes the signal processing society bigger. Otherwise, it's all numerical analysis, numerical things. Okay. But later on, speech processing, and then people want to generalize. So early day, you all look at all the key people in the signal processing. All early days, all speech processing guys. But later on, people try to add a two-dimensional signal processing and try to handle images. But now the way I look at that is image processing is so different from speech processing. Image processing is so different from the one-dimensional signal processing. So image processing has nothing to do with that. Image processing is really a separate family. Okay? It's really a separate family. So image processing, video processing is totally a separate family, and so on. And there's no need to use impulse response. Okay. In optics, actually, there is a so-called some similar point spread function. So in optics, there's called point spread function. So in that case, a point spread function is very similar to impulse response. So it's also consider if the input is just the impulse, and how you see the output, how you spread out. Usually it's a Gaussian. Okay, so the input is like a very, very narrow, sharp ray, right? The optical, the ray. And then the output will look like something spread out through a lens, right? And then spread out. So it's called the point spread function. So these two concepts, the same concept. Okay, but when I'm looking at the image processing, I prefer looking from another view. So the other view is you just consider the input, it's the input, and then you consider how you have the window, and how you weighting them, and how you averaging them, and get some output and write. So the output is just single pixels, but input is a group of pixels, a group of things, and you do the operation. Okay. So now the question is, what's the relationship between the two? So what's the relationship between the two? Can someone tell me this? What's the relationship? What? Yeah, in some sense, it's not necessary. It's not necessary. It's, if you have the energy preserving transform or energy preserving system, then energy will be the same. But it doesn't have to be that way. What? Yeah. Actually, that's the correct answer. So when you do the impulse response, actually, there is also a detour in terms of operation because the computation has to be convolution. So the general signal input you have using the general signal convolve with the impulse response to get output. But the operator mask, you don't have to worry about that. Operator mask just say, well, there's the input, I do just averaging, and I get the output. Okay. So anyway, let me try to explain this by using the mathematics. Okay. So actually, the impulse response or operator mask, they are all trying to handle one thing. It's like try to handle, particularly let's consider the linear time invariant or linear spatial invariant system. Or spatial. So time or space, okay. But let's look at 1D case. So suppose I have the a system. It's output, input, but it's satisfied us. So in order to consider time invariant or space invariant, I cannot have boundary condition. I need to go to minus infinity, plus infinity, okay, all the things. So then my output, we can write down this like y0, y minus 1, y minus 2, and then y1, y2, right? And similarly, I can do my x0 here, x minus 1 here, x minus 2 here, and this x1, x2. And if I look at the relationship between this guy and this, or this guy and this, there is if it's time invariant or space invariant, I can write down this as a Topliss matrix. Topliss matrix means all the, this called the diagonal terms will be a constant. That's called Topliss. Okay, so along this line, if you call this I, this is called J. All the ij is a constant. So this is ij, I subtract j, say it's 0, this one. And I can write down this like h0, h0. And this one is h minus 1. And then this one is h minus 2. Okay, minus 1, minus 2. And this is h1. It's h2. And you can continue go. So h0, h1, h2, h3, and h minus 1, h minus 2, and minus 3. So it just depends on how you read it. Okay? If you read this one, you want to find this output as x0, I can look this x0 as my center and look at this. And then this one, you read this is operator mask. So I put the mask on top of my input, this is my center, and give you the output. So this is called operator mask. You just multiply this, give you the. And what's the impulse response? Impulse response means you put these all zeros, you only look at this guy, and then this guy will read what? This guy will read this one. You read this one and you write out. That's called the impulse response. So this is the, if you need to look at this Topliss matrix, look at this row of Topliss matrix. And this will be the column, the impulse response. It's the column of this Topliss matrix. It happened to be, yeah, there's a way, when you read that, there's a reverse relationship. So when you put 1 and you get something like that, right? So you can prop the system. This is called H. Because you read this way, right? And this is H1, H2. So you read this column-wise, you read this row-wise, but the way you arrange this, if you look at this, it's H minus 2 minus 1, so right, read this way. But when you read this, actually you read it as impulse response like that. But then you have to do the operation. One is directly just multiply, but one you need to do the convolution. Okay. So you can write down what's the yn look like. It turns out you have to flip around. But I want to tell you is if you write down this top is matrix times a vector, give a vector, it's clearly just two ways. One is to consider just the one output element. It will be vector times vector. Okay? Or you consider one, the other are 0, and then you read one column and give you the result. So it's just about the row and column. But which one has more information? It's the same, right? Because why? Because the 45-degree line is all the same, right? This all topless means all this line is the same. So you go this, you can get everything out. You go this, you can get everything out. Because it's topless, so it's all diagonal term. So basically it's a 1D problem. It's a 1D, right? Okay, so if you want to do the summation, if the symmetric, you don't see the difference. But if you do the subtraction or you do non-symmetric filter, then the impulse response and the operator mask will be confusing. So whatever I read in the book is the impulse response. Whatever I teach in the class, it's the operator mask. And I want you to stick to my notation using operator mask. Operator mask is very simple. Just you don't have to do the swap and then multiply. So I just tell you what the coefficient look like, you just multiply, that's it. There's no need to do the so-called convolution. So convolution taken away from my class, okay? I don't like convolution. I don't need swap impulse response. We just do operator mask, direct multiply, and get output, that's it. This is more numerical analysis approach. This is because I have a lot of background in numerical analysis, I train as a numerical analyst. Also, I also train as a signal processing, but anyway, I prefer using the numerical analysis viewpoint, just operator mask. So we discretize the operator, and then using operate on the input, and output just 1 point. Any question about this? I mean, it's equivalent view. They are equivalent. So there's nothing really spatial. They are equivalent. But just somehow the way presenting the textbook just different from the way I present in the class. And I think the operator mask is much easier, more direct. There's no swap, whatever. Okay, so in edge detection, you see all the mask written in the book, it's all impulse response. But in my notation, all the operator mask, and there will be a -1, +1. You all swap. It turns out everything just swap. But you know the reason, because you apply the impulse response, you have to swap again. When you do convolution, you have to swap. So you become my operator mask. Okay? Okay, I think we'll stop. And the homework number 1, you got to start it. Okay, that's really a warning message. You got to start immediately. Okay, so we'll stop here.
This concludes Class EE 569 on Friday, September 6, 2013.